Okay, so welcome guys. We are going to solve the problem increasing subsequence. Okay, in this problem, you are given an array containing n integers. Your task is to determine the longest increasing subsequence in the array, the longest subsequence where every element is larger than the previous one. Okay, so let me first write down the example. 3, 5, 7. Guys, 7, 3, 5, 3, 6, 2, 9, 8. 7, 3, 5, 3, 6, 2, 9, 8. Okay, so let's start with this example. So what we have to find, we already know that what is it? We have to find longest increasing subsequence. We already know what is subsequence. Subsequence is any array formed from by removing certain elements from this, but the order must not change. For example, 3, 5, 6, and 9. This is the subsequence of this array. And this is also the largest one. Okay. So how can we find out this? So firstly, you can say that based on the previous methods, what we can do, we can maintain a TP of I, which will give us LIS ending at ith index. Okay, and ending at ith index, and we can update it by iterating to every element that is smaller than previous one. Okay, so this would be every element where uh, j is smaller than I and a of j is smaller than a of I, and we would simply take the max of that. We would take the max of this plus 1. Okay, so you can say that this would give us the answer. So what we are storing the LIS ending at ith index, and how we can update it. So suppose we have to find what is the largest LIS ending at 6. So how we can find it? We can look for 3 and ask him the same question, that what is the LIS largest increasing subsequence ending at this I. So that would be 1. So this would give us answer 2. Okay, so now we would move to 5. This is also smaller. So it will return 2. So here the answer would get updated to 3. Now again it will go to 6. But from, sorry, again it will go to 3. But now the answer is 1. So here the max is still 3. And it will go to 7. But 7 is not less than 6. So we would not consider it. Okay. So for 3, we get 6. And similarly, when we would reach 9, then 9 would ask 6 and it would get 4. 8 would also get 4. So at last, what we can do, we can return the, at last, what we can do, return maximum element of whole DP array. Okay. So, okay, so this, you are right, this can be done. But let's first look at the time complexity. Here, n is 2 to the power 5. 2 into 10 to the power 5. Okay. So, and our time complexity for this would be, it would be n square. Okay, so it would be 10 to the power 4 to the power 10. So it is way higher, way greater than, it is way greater than 10 to the power 8. Okay, so this would not work because for at every index we are looking for every index behind them. Now you can say that what if we just look the previous behind one, I mean smaller than just it. So for 6, what if we look for just 3? Then you can see that it would not get us optimal answer because if we just look at 3, it was giving us 2. Okay, so this was not optimal. Okay, so that will also fail. So now how can we think about it? Okay, let us write down. Let me copy the 7353629. 7353629. Okay. So let us do a dry run. Okay, so first element is 7. Okay, so this can be one alias. Okay, so 3. Now 3 can't be added here. So let us create a new alias. Okay, now 5. 5 can't be added here, but it can be added here. So let us add here. Now 3. 3 can't be added to anything. So we would make a new one. 6. 6 can be added here. It can be added here also. Okay, so we will add it. Now 2. 2 can't be added anywhere. So we would simply write 2. Make a new alias with 2. 9. 9 can be added here, here, here also, and here also. And 8. 8 cannot be added anywhere. So let's make a new one. Okay. So now these are the alias which we got. Okay. So what is the longest length? That is 4. That is of this. So now hear me. So what if we store alias that starts at certain number, uh, means and end at certain number with size. So what I'm saying is let us store the alias size wise. Okay, so alias of size 0 would be stored here. Of size alias of size 1 would be stored here. Alias of size 2 would be stored here. Alias of size 3 would be stored here. 4 would be stored here. 5 would be stored here, and 6 would be stored here. So now what we are finding that what is the best alias we can get for this value. Okay. Okay, so now let's see. Now for 1, wouldn't you say that if for 1, if we want alias of just size 1, so wouldn't you say that it would be better to just take 2? That is the smallest. So because it's just 1, and if any new number comes, then it would be easier to append it to 2 than rather than 7. Suppose here it was 10. Okay, so here suppose it was 10. Okay, just so take, let us think that here there were just 2 elements, that is 2 and 10. Okay, of size 1. So wouldn't it be best to take 2? Because now if any other element comes after this 2. Okay. Oh, and here one more thing, we are iterating in this order. Okay. So if another element comes, that is 9. So wouldn't it have more chances of appending to 2 than to 10, right? So what we are storing here, we are storing last element of subsequence of size I. So for first, we are storing the last element for any subsequence that end at index 1. So wouldn't it be best to store the lowest last index. Okay, so in that way, in future, if anything comes, we can append it. Okay, so let us store 2 here. Okay, now for for the size of 2, the size of 2 best one was 5. Okay, so wouldn't it be best if we write 5 here? Now we are not depending on this. Okay, the whole subarray which end at 5 is different. That is 3 comma 5. It have nothing to do with the 2. Okay, what I am just storing? I am just storing the last index of the of all the subsequences with size 2. So this would be also a subsequence of size 2, 3, and 5, and I am storing the last. Now, why I am storing the last element? Now, suppose if a new index come. Okay, so for 2 we can also create 3 or 6. But why we have chosen 5 only? Now, suppose the next element 6 comes. Okay, so we can see that it is possible to make 2 with 5. Okay, it doesn't matter that if here in between here there was a 7. Okay, or it in between here was 4. What I'm trying to say that the lowest candidate would have the best possible best chances of getting expanded. Now suppose we don't know what are the upcoming. We are iterating till here and we don't know what are the upcoming elements. Okay, but we know all the elements which came before that, and we are maintaining an array which stores the last index of any last index of subsequence ending at that element of a fixed sizes for size 1, 2, 3, 4, etc. So for any particular value, wouldn't it be best to take the smallest one? Because if any new number comes, let's say till now we have size of 3, and the two possible ways were 3, 5, 6, and 3, 6, 9. Okay. So what if we had stored 9? So now if again a 9 comes, then we can't append it to 9. But what if we have chosen this subsequence? So when a new 9 comes, we can new 9 came, we can append it to this. So the lowest element would have the maximum probability of getting expanded. Okay. So what can I say? 7, 3, 5, 3, 6, 2, 9, 8. Okay, so this was the question. Let us try one more time. Now what we are doing? Getting one of size. These are the sizes. We can say this is our current alias. Okay. Now what it came? Now new element came 3. So it can't be appended to the current alias because it's smaller. But wouldn't I have better chances if I replace this 7 with 3? Because if element greater than 7 comes, suppose 8, then the answer would be no different for 7 also and for 3 also. But if the next element was 4, then the answer would be always better for this smaller element. So wouldn't it be best if I replace this 3? Yeah, I replaced it. Now 5. So 5 can be appended to this alias. Okay. So now what this stores? This stored the size or maximum alias ending at 5 for size 2. Now again 3. 3 can't be appended here. 3 can't be appended here. So we can't make the we can't put 3 here because previous element is also 3. Okay, so 3 can't be replaced. Now 6. Okay, so we can append 6 here. Okay, we appended. Now comes 2. Okay, so 2 would not come. But now if we take 2 here, we would replace 2 here. Why? Because for one index, 2 is the best option to get appended. Okay, as I said, Even if what if 4 comes here after this? So 3 would also have opened at 4 and 2 would also have opened at 4. But if 3 came, then 3 cannot append 3, but 2 would have appended 3. So for that current size, we would replace that as 2. So now what from this what can we derive? There is a one uh, there is a subsequence of size 1 which can end at 2. There is a subsequence of size 2 which can end at 5. There is a subsequence which can end at 6. So okay, so this is the case. Now what now 9 came, so 9 can be appended. So 9 would be added here. Now 8. So let us say there are currently what is the highest? 3, 5, 6, 9. This is the highest 4 length we got. Now if we can update this 9 to 8. Okay. Now why it would be better? Because if another 9 came, we can append it. Okay. So that's why now what is the best case which end at 4? That would be 8. Okay, so answer would be 4. And this would be always in increasing order. What I mean by that is, okay, this is not the alias. Okay, don't consider this alias. This is showing the best alias which can get that end at 2, size 1, and size 2 end at 5, size 3 end at 6, and size 4 end at 8. So what we are storing, we are instead of storing the whole alias of every size, we are just storing earlier what we did here. We were storing the whole alias. Okay. But now instead of storing the whole alias, what we are doing, let us first look at how new element can update the previous aliases. Let's say there were few aliases. Okay. So and if we are only looking for size. Okay. So if there was an alias of size 3 and there are multiple aliases of size 3. Okay. Now if a new element came, which can increase the size of this alias and this alias also. So it would be same. Now the new alias would have size 4. Okay. Now what if it makes the new alias of size 3? Okay. Suppose 256, 257, and 258. All three are alias. So it would be best to append it. Okay. But where we can append it? Which would be best? Now if we can append to 6, append the addition of a new element in any alias just depends on the last element. We don't care what its element were before 6. Okay, here also we don't care what it elements were before 7. Here also we don't care what it elements were before it. We just care about the last element of that alias to add to see if we can add that or not. Now we want the longest subsequence. So whenever we can add it, we would add it. Okay. So now any subsequence of size 3 can be made to 4 if we add it to add a new element to it, or if we replace any element to it, then it would be 3 only. Okay, it can never decrease. The size of any alias would never decrease. So suppose there are few examples, 2, 5. So adding of a new element will only increase its size. Okay, or if it's 7 or something like that, if it's 5, if we can't increase, then what we can update. Okay, but we can never decrease any size. Like if there is a alias of size 3, we can't decrease it. Okay, so well, that's why we are just storing the last element because it only depends on last element. So now this, if you see this, vector will give us every possible LIS we have currently. But instead of having all the LISs, we are just storing what part is necessary. So what this part shows, there is a LIS of size 1 which would end at 2. This will show there is a LIS of size 2. We don't care about what was the first element, but this ends at 5. Now there is a LIS which ends at 6. So we don't care what its last two elements are. We just care about the 6. And now we have LIS of 4, which ends at 8. Okay, so this shows us this. This is all the information we need to make any new improvement. Suppose if we got 9, then we can get a new LIS that can be of length 9. We can append it to 8 only. Okay, so now we got a new LIS that is of length 9. Okay, suppose if we got 7. Okay, so now no new LIS can be formed. Actually, a new LIS can be formed of size 4 that can be appended here, so it would become 7. So now we already have a LIS of size 4. Okay, so what we will do, actually it's a improvement, because as I said, it's better for LISs of same size, it's better to take the one which has lowest last number. So this 8 would be replaced to 7. So now again we have this many LISs. Okay, suppose a new number comes, that is 11. So that is let's say, yes, that is of 11. That is 3. Okay, let's say a new number came, that is of 3. Now we can't append it to any of these LISs, but we can append it to the LIS of size 2, size 1, because it is lower than this 3. So if we append it to 2, it would become 2 3. Now its size is changed to 2. Okay, so now we don't care about what is the previous elements. We forget about the 2. So now we would update the change towards the size of 2. So now this is smaller. So we would update it to 3. Because now if a 4 came, we can update it to this. Okay, and it would also update this 4. I hope you are getting. So what we are storing at any point, we are storing last number of LIS of size I. Okay, this is what we are storing. And this is all we need to get the best possible answer. Now, how can we fill up this? Let's say 73536298. Now, how can we fill up this? So this can be filled up in increasing. Let's say how. Let's see how are we going to fill up this. So first 7. So it's empty. So currently add 7 to our vector. Now it's 3. So now we can't simply append it. Okay. So what can we do? We can do a binary search. What we can do? We can do a binary search on this vector, and it will give us. We can do upper bound. So what it will give us? It will give us the index of element just greater than 3. Okay. So index just greater than 3 would be 0, and here we would append it 3, because now the LIS with size 1 is best case is 3. Now 5 we can append it. We would have appended it. Now again it's 3, so we can't do anything. 6 we can append it. Now 2, binary search on this, and we would find out that Now the best case for size 1 was not 3. Now the best case for size 1 is 2. Okay. Now 9, we can append it. Now 8, so we would replace this because upper bound will give us 9 and we would replace this with 8. Okay, so what is the maximum size we got? It was 4. Now you will see that it will always stay increasing order only. Okay, it will always stay in increasing order. Now, how can I explain that? You can see no, because if it's not, we are never, we are only replacing any element that is smaller. Means we are never actually adding a element that is. We can't append any element that is smaller than 8 to its next. Okay, so we are only replacing the biggest element we found. Okay, so that is how we are doing. So what is the algorithm? So first, what we will iterate from I equal to 0 to I less than n, I plus plus. Now we can do a upper bound on vector. Initially, it would be empty. Let's say vector of answer, or DP vector. Okay. So if this is iterator, if this iterator is ending, means there exists no element which is greater than this element, then we can append it to our current answer. Okay. Or else, what we can do, we can replace that iterator with this element. And at last, what we will do, we will return size of this current DP. Okay. So this is our algo for this. I hope you understood what I was trying to say. Okay, so this was the whole explanation for this. Now let's look into the code of this. We'll take the input. We will define a DP vector. Now what this DP of I would give us last element of LIS of size I plus 1. Okay, so smallest. So now for every element, what we would do, we would do per bound on DP with this value. Now if it equal to ending, then we can push back this way. value to our answer, or else the answer of this iterator would be 0, 5. And we would see out our answer, that is dp dot size. Okay, so that is for time complexity would be and log n, because time complexity for it would be n log n, because for every element we are doing a binary search, and it will get maximum log n. It has a maximum time complexity of log n, so the size of this vector can go maximum to n, so it would be log n. So this is our proof. Let us put that, please. Okay, so we can also take, okay. So what we did here wrong was we thought that it should be strictly increasing, but it should not be decreasing. So it can be either be equal to or greater than that element. Okay, so sorry, in my in our solution it took equal means in our solution what it did was yes, sorry, my mistake. What I said, in our solution, what we are doing was correct. We have to find the longest increase in subsequence, but in our answer solution, what we did, we find the longest non-decreasing subsequence. So equal to was also counted. So for this, what we can do, we can find the lower bound. So what this lower bound will give us, the lower bound will give us, if the value is already present, then it would give us the index of that element. So that would not change the answer. Okay, so let us make this. Okay, so it got accepted. So that was it, guys, for today. So what? So you understood why the upper one was not giving us the right answer. So what it was doing? Suppose the answer is one. The best case for the current is one. So what our answer was doing? The upper one here would be here. So it was appending it here. But actually this is not a valid subsequence. So what it should do? If the element is already present, then it should return the index of that element. So that's why we used lower one. Okay. Let's see what was the intended solution for this. Okay, so it's only okay. So they did the lower bound. Okay, so they already predefined the best. Okay, so they did the same only what we did. Okay, if you guys want, you can also see the solution. I insist you that you should see the solutions of this after you solved it on your own, because sometimes what it can give us, it can give you some unique ways, unique alternate ways also, which can be better from your way also. So the first method they used was segment tree. I think there was no need for segment tree in this. Okay. Okay. So see you in the next video.